Hello, this is topic 2. In this topic, we are going to have a look in the interaction of radiation with matter and of course radiation scattering. There are only two interactions that are important in radiology. One is how photons interact with matter, and the other is how electrons interact with matter. These are those two that are important because photons interact with matters, produces electrons or eject electrons out, and there'll be photoelectron, Compton electron. So there'll be electrons, and this electron will be further interacting with human tissue. So that's why the two important interactions involve photons and electron. So what is so important and what ought to be studied of these two interactions? Number one is the attenuation properties, number two the absorption properties, and number three the scattering properties. Other interactions such as the one with the nuclei vibrating the electron are not quite considered in this topic because it is not an interaction that produce the different level shade of grays in imaging. In these two interactions, photons and electrons, the behaviors are quite different, vast different. For photons, as it interacts with matters, photon would normally have no interaction, one or a few interactions, and photons are exponentially attenuated. Photons interaction with one atom or with individual interaction is expressed in terms of cross sections, the cross section of the interaction. However, the attenuations for photons through a bulk, a mass, a big chunk of media is expressed in terms of its attenuation coefficient. However, electrons experience large number of interactions. It normally gradually loses its energy as it being stopped or incident onto a photon, and the expression of electrons interaction is always defined in terms of the electron range or the stopping power. In the context of radiology, there are four main interactions that need to be considered. Number one is photoelectric interaction. Number two, coherent scattering. Number three, incoherent scattering. And finally, pair production. But in radiology, only the first three that are important, because for pair production to occur, the incoming photons must possess energy at least 1.02 MeV. Diagnostic energy ranged up to only maximum 140 keV. That means we're setting the generator to 150 kVp. So therefore, pair production or triplet production is not important in radiology, but this interaction occurs as if we are talking about photons interaction with matters. Pair production would occur for higher energy photons. Specific cross-section symbols are associated with each interaction. For photoelectric, it's tau. Coherent is psi coherent. Incoherent is psi with subscript incoherent. It's tau. Sigma, it's lowercase, small letters. Sigma coherent, sigma incoherent, and kappa for pair production. So only the first three that are important in diagnostic range of energy. But mind you, as photon interacts at higher energy, pair production or triplet production would actually occur. And as these photons interact with atom via these three interactions, this will result in scattered X-ray if Compton scattering occurs, characteristic X-ray if photoelectric occurs, annihilation if pair production occurs. Of course, in our case here, we don't annihilate because we're working only up to Compton scattering. When X-ray or gamma photons interact as a beam through a bulk of media, there are only three possible outcomes from that. One, there will be no interaction. All photons are transmitted through the media. Second, there will be an absorption. Parts of the energy is transferred. Absorption is a total energy is absorbed by the electrons, and a little energy is needed to overcome the binding energy. And of course, the photons can be scattered when it interacts near the nucleus of the atom or by interacting with one of the outer shell electrons. These two are known as attenuation. So photons can be attenuated via two methods, absorption and scattering. Let's go through the first interaction, photoelectric interaction. In photoelectric interaction, the photon that incident with an atom will leave the atom in an excited state. The excess energy is released when one of the electron is ejected, and this electron is called or known as photoelectron. It leaves the atom with a kinetic energy received from the photons. The energy transferred to the atom is very small, and this can easily be neglected. So we are assuming that the energy is transferred fully to this electron. The photoelectric effect can only occur if the incoming photon has an energy exceeding or more than the binding energy of the electron of that particular shell. So it must have more energy than the binding energy of the electron that it wants to eject. So the electron that is leaving the atom has a kinetic energy equivalent to the hv, which is h constant, Planck's constant, and v is the frequency of the photons, minus the binding energy of the electron shell from where the electron comes from. Photoelectric fits in one probability at where number one, the incoming photon must possess energy with higher energy of the binding energy of that electron, and also normally photoelectric interaction occurs with an electron with the highest binding energy of that particular atom. So normally it occurs with K shell electron. Although it sounds simple, but let's have a look into when photoelectric interaction most likely occur into a little bit more closer. Let's have a look at this. This is atomic cross-section data for photoelectric process of three different elements: tungsten, molybdenum, and copper. They have each have got different atomic number, and this cross-section is plotted against the energy of photon, and this is done on a log scale, and the energy range from 1 until up to few hundreds here. What can we observe from this figure? They are sharp sharp rise, or we call sharp increase in band in cross section. For tungsten, we can see the sharp rise is here. Oh, sorry, which one is tungsten? Tungsten is this. This is the sharp. This is not so sharp. And then secondly, this is for molybdenum, sharp. And then finally for copper, sharp. We can tell that the the cross section has risen. The sharp increase in cross section, the coefficient of this rise per atom in an atom is only, so you can tell that the difference is only high for a certain peak, and this is actually representing the K shell edge or K edge absorption. There are other rise, but it is not so high. So the increase is not so high. So we can tell when the energy of the incoming photon is close to the K shell binding energy or the K edge, there will be a sharp increase or higher increase of absorption. It could be for tungsten, molybdenum, or copper, for any material for that matter being said. For other shells, these are the binding energy or the LH, the MH. For others, the rise is not so high, it's just a little bit, but here you can tell it's a strong increase or a higher increase. So this sharp peak representing the position of the absorption edges for different material depending on the orbital or the shells, the K shell, L shell, M shell. So at where they are peaks, that means it representing the KH, LH, MH, or the edge energy for absorption. So if you look into tungsten, the discontinuity occurs at 69.5 keV. That is the exact value. And this is representing the K shell binding energy. At an energy just less than this, the cross section is 6.4 times 10 to power 2 bond per atom. While just slightly above this energy, the coefficient is at about 3.3, 10 to the power 3 bond per atom. In a way, this represents a sudden increase of cross section at about a factor of 5 when the photon energy increase above the K shell. So therefore, photoelectric interaction is more probable when the electron binding energy is slightly less than the energy of the incoming photon, or the energy of the incoming photon is slightly more than the binding energy. When the energy keep increasing, the cross section decrease again, or the interaction decrease again. So this interaction is possible only when the photon has sufficient energy to overcome the binding energy, and then the cross section will then decrease again. And if we keep looking into this figure, we can tell there is another one for tungsten at 10. This representing the LH or binding energy for L shell, and then another one at M shell, and this is the about less than 2.5, 2 to 3 keV, and they are rough peaks or rough edges here because at L and M they have more sub levels, as we've seen in previous lecture. That's why it's a little bit more complex depending on from which sub-levels the electron comes from and so on. So this explains when is photoelectric most probably gonna occur within an atom. So the photon, the incoming photon, disappears in photoelectric interaction. After the interaction, there will be a vacancy because the vacancy is left by an electron that has been ejected out. And this vacancy will be filled by another electron from outer shell or higher shell, and the difference between these two shells will produce fluorescent X-ray or characteristic X-ray. So when photons interacting with human tissue, depending on the K binding energy and L binding energy of human tissue, there'll be fluorescent X-ray or characteristic X-ray will be produced within human tissue, that the target is human tissue. Or instead of if this fluorescent X-ray being able to be ejected out, so it will be exiting human tissue as characteristic X-ray, but it's very unlikely because this characteristic X-ray has very low energy because K binding energy, L binding energy of human tissue is quite low. So most likely this fluorescent X-ray or characteristic X-ray photon that was produced within human tissue or within subject matter will hit, the energy will be absorbed by another electron within that atom, and these will eject out an OJ electron. And after the initial vacancy is filled, the new vacancy will then be filled again, and there will be a cascade of events as what we've seen earlier, and finally leave the atom in a highly ionized state. Based on the previous figure, this would be the best summary to explain what does it mean by the different fluorescent X-ray coming up from a photoelectric interaction. All the energy from the incoming photon will be transferred to two different components. One, to overcome the binding energy of the K-shell electron, and two is to deliver or gives out or transfer the energy to the electron, and this electron will be ejected out with a kinetic energy. So as an example here, say this atom has a binding energy of 34. This 100 keV incoming photon has to overcome this binding energy, and the rest of the energy will be transferred to the electron, and this electron will be ejected out as a photoelectron. So an empty shell immediately is then filled. So there will be a vacancy, and this vacancy will be filled by an electron from outer orbitals, and these orbitals, this is not E gamma, E X-ray. X-ray. So I'll just correct that. Oh, I cannot mix ups. Okay. So when the incoming photon interacts with the electron, leaves a vacancy. Through this interaction, the second stage, this vacancy will then be filled by electron from outer shell, and this outer shell has a different binding energies, and the difference between these two binding energy will produce a fluorescent X-ray or characteristic X-ray. So if this is human tissue, the fluorescent X-ray is equivalent to the K shell binding energy minus the L shell binding energy of human tissue, soft tissue, whatever tissue. So for example, the iodine, K shell is 34, L shell is 5, and M shell is 0.6. If there is a vacancy at K shell, the fluorescent X-ray, if the electron is being filled by the L shell electron, this produces photons at 34 minus 5, meaning this energy is equivalent to 29 keV. If it's being the vacancy occurs at L shell, and then if the electron is being filled by the M shell, it will be 5 minus 0.6. So these photons, or the fluorescent X-ray, has energy 4.4 keV. So if you see correctly, most of this energy of the cascade OJ electron, or the cascade of photons, these energy are too low. Most of these photons, if it occurs within human tissue, it will be self-absorbed by the human tissue, so it actually incurred dose to the patient. Some of these photons will interact with the other electrons, and this electron will be ejected and known as OJ electron. What photoelectric interaction depending to? So what are the variables that controls or affect the photoelectric absorption or photoelectric interaction? Number one is the binding energy. So binding energy defines if photoelectric can occur. If the binding energy is higher than the incoming photon, photoelectric most likely not gonna occur. And binding energy is directly proportional to the atomic number to power 2. The higher the Z is, the higher the binding energy of the K electron. So number 2, the probability of photoelectric interaction is directly proportional to the atomic number to power 3. So with a slight difference of atomic number, there will be a huge difference in photoelectric absorption or photoelectric interaction, because it is directly proportional to atomic number to the power 3. So let's say you have two elements with one with an atomic number 4. So 4 to power 3 the 4 to power 3, the probability is at about 64. But if the atomic number is 5, the probability goes up to 1 to 5. So 1 to 5 to 64 is a huge difference, although the atomic number increased by only 1. And the photoelectric absorption is inversely proportional to the energy. So let's have a look here. We've seen this figure before. These are three different elements with tungsten, molybdenum and copper, with tungsten having the highest atomic number. The cross section for tungsten, say at 60 keV, let's say this is at 60 keV, is the highest compared to molybdenum, and the lowest being copper. The higher the atomic number, the higher the cross section for photoelectric interaction. However, as the energy increases, the photoelectric interaction decreases. Just have a look at tungsten. As the energy increases, the cross section is decreasing. So these are the variables that affect photoelectric absorption. Okay, let's have a look at a much better example as what I mean by KH absorption. These are photoelectric interactions occurs with photons. This is actually true for gamma photons or X-ray photon, but in our context in radiology we are using X-ray photons. So let's imagine this is X-ray photons, and these interactions, the photoelectric interaction is observed in terms of the attenuation coefficient. So as gamma photons at and various energy in the range from 10 keV up to 10 MeV interacting with copper and tungsten. Photoelectric, Compton scattering, and pair production interaction occurs. But in this particular section, we are going only to have a look specifically on photoelectric interaction. So as the photons interact with the element, when it reaches to the KH, or the binding energy for the K shell, there'll be a sharp increase in terms of the attenuation. So the attenuation increase, say this is 30, from 30 up to 100, or let's say this is 200. So it's about 170 per centimeter. Because photoelectric is more likely to occur when the incoming photons has energy slightly above the KH. So the KH is 69, so this is at about 69. There'll be a sharp increase, but when the energy keep increasing, when the energy of the photon keep increasing, the linear attenuation, the attenuation through photoelectric interaction, decrease again. And there'll be another sharp increase at other edge. So this is LH at 12. There is a sharp increase. So this is 500. Let's say this is 600. More than, let's say this is 3000. So 3000 minus 600 at about 2400. So photoelectric is more likely to occur when the energy is slightly above the binding energy and the attenuation decreases with energy. But the energy is the photoelectric interaction is inversely proportional to the energy or the incoming photon. As the energy increases, the photoelectric effect decreases. So let's say at 5 MeV, the linear attenuation coefficient is about 0.04. At 1 MeV, about 0.5. At 0.1 MeV, at about 200 attenuation coefficient per centimeter. So it fulfills of whatever that I've explained in the previous slides. As for copper, because the KH for copper is 8.98 and the minimum energy being observed here is 10 keV, you are unable to see the sharp increase. But if we did observe to less than 10 keV, there'll be a sharp increase at 8.9 keV and then start to decrease again. So as the energy decreases, increases, photoelectric interaction decreases. So less likely photoelectric interaction would occur with low atomic number materials. So photoelectric interaction is directly proportional to Z power 3. So Z to power 3, this is low Z, higher Z. So the photoelectric interaction is higher. If you look into all the area under the curve, it's higher compared to the area under the curve for photoelectric interaction of copper. As a summary to that, we understand up to now that the energy of the incoming photon is completely transferred to the atom. The one is transferred to overcome the binding energy, and the rest is transferred to the electron, and there will be no more photons, there will be no more incoming photon, and the incoming photons interact with an orbital electron, usually the K shell electron, and then the orbital electron is dislodged out, and the energy of the incoming photon must be equal to the binding energy of the electron, or most likely slightly more for photoelectric interaction to occur. So when the photon ceases to exist, now the energy is given to the ejected electron out, the electron that being ejected, and this photoelectron now has the energy to interact with other atoms or with other electron, and this interaction resulted in increase of patient dose and contributing to nothing but biological damage to the patient. So this summarizes what photoelectric effect is. By looking at this figure, at this moment you should be able to explain the interaction of photon with the K-shell electron and the production of fluorescent X-ray. So you should be able to explain this by looking at this figure. And the vacancy will being filled by other electrons from outer shell, and this produces characteristic photons. But for human tissue, where the KH, LH, MH are very low, the characteristic photons produced are also relatively very low, and these energies are normally absorbed within the tissue and known as nothing. It's as just more dose to your patients. So this figure best explains the production of fluorescent X-ray within human tissue or within any subject matter, as the vacancy at K-shell being filled by electron from outer shell and filling this shell, building this vacancy, and this produces cascades of characteristic photons. Photoelectric is normally dominant process of X-ray absorption only to energy up to 500. After that, it's no longer dominant, or other process or other interaction takes charge, which is Compton until 1.02 MeV LB per production. The X-ray that is completely absorbed by the atom, then that is cease to exist, explains the importance of KH in the absorption of incoming photons. And the understanding from KH explains how KH absorption being significant and various stage of radiology. Number one, way after, it's I think topic number 4, I think, or topic 4. Because of the KH absorption, for two different tissues that has similar atomic number at where the difference in terms of the density is very low, the tissue can be highlighted by tagging the material with high Z number material. For example, iodine, barium is all among the two solutions that is used to increase the atomic number for a particular tissue. For blood, so blood can be tagged with iodine, so blood has atomic number close to soft tissue, so you weren't able to see that. By having higher atomic number of blood, there'll be higher absorption. There'll be that will finally show the difference in terms of level shade of grays. So these are among the two materials that are used as contrast agent. So at KVP setting 150 with effective energy 50 keV, or 50 to 60 keV, these photons will be highly absorbed through photoelectric interaction. So therefore, it will show different level shade of grays compared to the tract or the GI tract. Barium is used as a tagging material in GI tract imaging. Other than that, because of the understanding in KH, different materials were used for intensifying screens in screen film technology, for the CR plate and so on. So don't worry about this. We're going to have a look into this a little bit more details when we comes to the subsequent topics or the subsequent chapter. But one thing to note is that energy less than 50 keV, at this energy, 50 and low, the photoelectric effect plays an important role in imaging soft tissue, amplifying small differences in tissue with slightly different Z. So if you are imaging breast, for example, you have got glandular tissue and then you get adipose tissue. These two tissues have similar density or similar atomic number. Therefore, if you work on to high energy, there'll be less probability of photoelectric interaction. So therefore, the lower the energy, the higher the photoelectric interaction. So if we go back to here, the lower the energy, the higher the photoelectric interaction will be. So therefore, the lower the energy, the higher the differences will be shown in your image. However, low energy, high absorption will cause or directly cause higher absorbed dose to your patient. So after the photoelectric interaction occurs, there will be no more photons. Remember that photon is not a particle, but it's a wave with energy, but it almost act like a particle. So when the energy of the photon is all transferred, there will be nothing more of the photons that would cause further ionization. So this summarizes when photoelectric will occur. When the initial incoming photons has energy less than binding energy of the K shell electron, the photoelectric with K shell electron would not occur because it needs more energy to overcome the binding energy of that particular electron. So as this photoelectric interaction is impossible with K shell electron, photoelectric might still occur with outer shell electron. Unlikely, but it can still occur for as long as the energy is close or higher to the binding energy with L shell electrons, M shell electrons, and so on. When the energy of the incoming photon is close or equal to binding energy of the K shell electron, the electron may be ejected, or there'll be a probability for photoelectric interactions to occur. So the threshold is the binding energy itself, and the binding energy is directly proportional to Z power 2. So binding energy is depending on the atomic number of that particular atom and the shell. Which shell? The lower the shell, the outer shell has lesser binding energy. And photoelectric effect most likely to occur when photon energy is close to binding energy or more than the binding energy of the K shell electron. Okay, what are the factors that affect probability of photoelectric interaction? Number one, the incoming energy of the photons. Number two, atomic number of the atom or the target or the subject media. Number three, as the energy increases and the number of atomic number increases of the subject matter, the probability of photoelectric increase. As the energy decrease. If you remember all the figures that I've shown earlier, as the energy increases, the photoelectric interaction decreases. So you have we had a look into that in terms of the cross section or the attenuation coefficient. And as the atomic number increases of the subject being irradiated, the photoelectric interaction increases. When the electron is more tightly bound in its orbit, so probability of photoelectric interactions normally occur with the most tightly bound electron. So normally photoelectric interaction occurs to K shell electron. So when the incoming photon's energy has more or close to equivalent or more energy to the binding energy of the orbital electron, there will be high chance for the photoelectric interactions to occur. And these types of interaction is prevalent in the diagnostic kVp range from 30 to 150 kVp. So according to this context, bones have density or atomic number higher than soft tissue. Soft tissue has an atomic number or density higher than air. So air tissue, that includes your nose canal, esophagus, your lungs, for example. Soft tissue is lower abdomen. Bones, they're bones. So at high atomic number material, there'll be higher photoelectric, therefore there'll be more absorption, therefore bones appear white on computed radiography images or on film. Soft tissue allows more radiation to pass, more photons are being transmitted, so these structures normally appear gray on film or on images. Air normally allows all the photons to be transmitted through, and therefore these structures appear black on images. Those are the reasons why. But we are going to look how images being produced and what are the interactions that produces images, but this is in a much later topic. But I just would like to share how does the atomic number of subject medium affect the gray shade of images. So as into which interaction will dominate, it depends on the atomic number and the energy of the incoming photon. You can tell here that the photoelectric interaction is dominant at low energy. At medium energy, Compton electric interactions are more dominant, and pair production is more dominant when the energy is more than 1 MeV. So let's say the incoming photons, a radiographic imaging acquisition was set to 150 kVp. 150 kVp, the maximum energy is 150 keV with effective energy 1/3 of the maximum being 50 keV, and 50 keV is here. Therefore, for soft tissue with atomic number 7, let's say this is 7, the dominant interaction in soft tissue is Compton. However, for denser or tissue with higher atomic number, let's say 12 for bones, at 50 keV effective energy, the dominant interaction will be photoelectric. So depending on the energy of the incoming photon and the atomic number of the tissues, it defines which of these two interactions will be dominant in the interactions. So this being an example with an incoming energy, the maximum 100 keV, 100 kVp. So let's say the tissue is lung and the atomic number is 7.4. The dominant interaction would be 33. Effective energy would be 33. 33 is somewhere here. The dominant interaction would be Compton scattering as X-ray photons set at this kVp interact with lung. Beside the Compton interaction, the other interaction would be photoelectric, but the dominant one would be Compton. The same kVp setting with 100 keV maximum, effective energy 33. So at 33, let's say this is 33. Interacting with bone tissue with atomic number 12, so let's say this is 12, the photoelectric interaction is the dominant interaction. Else than photoelectric interaction, there will be other interaction. It's known as Compton. So the two interaction will occur with that tissue, bone tissue, but the dominant interaction will be photoelectric. Now let's have a look at scattering interaction. There are three related processes. Number one is Thomson scattering or classical scattering. This is a photon interaction with an electron. Then you have Compton scattering, photon with also electron. And then finally we have coherent which is Rayleigh scattering, which is photon interaction with atom. Thomson and Rayleigh scattering are elastic in a way that only the direction of the photons change, but the wavelength, the energy remains the same. And Thomson and Rayleigh are only important at low energies. It is not quite significant in radiology because the energy that we are utilizing is quite high, 50, 30 keV and so on. So what is Thomson scattering? In Thomson scattering, electromagnetic energy, or in our case X-ray, with a certain frequency incident onto an electron. And during this incident, the electron will emit waves of energy at the same frequency in the same phase as how the incident X-ray is. This electron absorb energy from the X-ray and scatter it to a different direction. In particular, for Thomson scattering, the wavelength of the scattered wave is the same as the one of the incident X-ray. Next, the coherent scattering or Rayleigh scattering. This derivation is expressed from the Thomson scattering, at where in Thomson scattering the electron that was incident with the photon was assumed to be free, alone and at rest. In reality, photon is scattered collectively by atomic electrons, the whole electron, and these electrons are not free, and their proximity to one and another is not very different from the wavelength of the radiation. So in coherent scattering, again, no energy is lost, and photons transfer all its momentums to the atom. Strictly speaking, the condition no change in photon energy applies to the initial frame, at which the total momentum of atom plus photon is 0. So in coherent scattering, no energy is lost. So the photons interact with the collective electrons in the atom, and then through this absorption, another energy is emitted out and scattered through at an angle theta, and this scattering by different electron is in phase with the incident X-ray. The coherent factor for Rayleigh is depending on the atomic number of an element. If an element is of a higher atomic number element, the number of electrons also increase. When there are too many electrons, the coherent factor, or the factor for Rayleigh scattering to occur, would decrease, because it is becoming increasingly difficult for these photons to overcome all these electrons of high atomic number atom without transferring the energy, because in Rayleigh there will be no energy transfer. So for that to occur, most of the time the atom must be of low atomic number atom. And finally, the Compton scattering, at where the scattering is significant in radiographic imaging. Like Thomson scattering, the Compton scattering is an interaction of photon that is incident with an electron. But in this case, for Compton scattering, energy is transferred to this electron, contrary to the Thomson scattering, no energy transfer, but in this case energy is transferred to this electron. The energy range is derived based on the theta angle and the psi angle of the interaction. The theta angle is where the scattered photon, the angle at where the scattered photon will be scattered away from the initial direction, and the psi angle is the angle of the recoil Compton electron. This is the geometrical arrangement of Compton scattering interaction, where the photon is coming from the left with an energy hv and momentum hv over c. And like when the collision occurs with an electron, the electron will be ejected out, and the photon will be scattered at an angle theta with an energy hv and the momentum of the with the momentum hv over c. The recoil Compton electron is ejected out at an angle psi with a kinetic energy, the remaining energy. So the energy here plus the energy here should equivalent to the initial energy. What is the relation of the scattered photons to the incident photon? The scattered photon hv prime to the incident photon, the ratio of the incident photon is equivalent to this, at where alpha is the dimensionless ratio, and the scattered electron here has a kinetic energy given by this formula. In a Compton scattering within the diagnostic energy range up to 150 keV, the parameter alpha is normally small, and for that reason the energy transfer to this Compton electron is normally also small. If the electron is forwarded to the direct direction, the energy is almost zero. And when the scattered photon is backscattered to the other direction, the energy of this electron is higher. So this is demonstrated here. So if you're working with X-ray photon from low to high energy, what is the expected energy transfer to the recoil Compton electron? Would it be higher or lower? The higher the energy of the incident photon, the higher the energy or the kinetic energy attained by the recoil Compton electron. Okay, in Compton scattering, as the X-ray photon is deflected with a much lesser energy, it retains most of its original energy and exits the body as an energetic scattered photon, because the energy transferred to the electron is always very low or near to zero, as I said earlier. So most of these photons will actually have the energy to penetrated out of the patient and become scattered photon that might endanger the personnel or the patients or whoever that are in the X-ray room. So since the scattered photon can exit the body, it does not affect the patient that much unless it is backscattered back to the patient, but it is more a bigger contribution to pose hazard to personnel, to the staff, and also what is more important in radiography, the scattered photon will reduce the quality of the image if the scattered photon can be absorbed by your film screen, your CR plate, by your digital detector, and so on. It will reduce the quality of the produced radiographic image. So let's have a look at this example at where you have an X-ray tube emitting photons to the patients, and within this patient photoelectric and Compton scattering occur, and because of the Compton scattering interaction, photons are scattered away from the initial direction of the initial photon. So the initial direction is to the floor, but the scattered photons are directed away from the initial direction. Some might reach to the personnel, some would reach to the wall and back scattered to the radiographers, or some might reach to your film, and so on. So this is the event and the consequence of Compton scattering. It produces scattered photons. Okay, when does this occur? It normally dominant in between 30 keV up to 30 MeV. Of course, this is depending on the atomic number or the density of the tissue itself. It occurs between photons and a free electron, an outer shell electron. So Compton scattering rarely occurs with tightly bound electron like photoelectric. It occurs with more freely or loosely bound electron, outer shell electron. So outer shell electrons are not tightly bound. The binding energy is also less. For as long as the energy, and of course this is X-ray. I have to correct that. Alright, for as long as the energy of the incoming photon can overcome the binding energy of the outer shell electron, Compton scattering interaction can occur. So basically the atom is ionized and the energy is distributed into Compton electron and the scattered photon, with the scattered photon has higher lambda lower energy compared to the incident photons. In general speaking, Compton scattering is depending on the density of the atom. The higher the density, the higher the electron density per centimeter cubic or per gram. The higher the number of electrons in a gram, the higher the chance for these incoming photons to interact with the electron via Compton scattering, and the conservation energy and momentum following this equation at where the initial energy is equivalent to the scattered photon plus the kinetic energy of this electron, or the recall Compton electron. Alright, these are the two figures that best explains how the scattering angle being affected by the energy. What actually happens if you are working from the lowest energy, or Compton scattering in MAMO, for example, compared to Compton scattering in HIP imaging procedure? What are the difference in terms of the Compton scattering within the tissue? So as the initial energy increases, high energy, both photons and electrons are scattered in the forward direction. You can see for 140 kV and 20 kV, the probability of the scattering angle is small for 140 kV, but for 20 kV the scattering angle is large or higher. a given angle fraction of energy transferred to the scattered photon, it decreases when the energy increases. So the angle always decreases with energy. The higher the energy, the more forward direction the scattered photon would be and the Compton electron would be. For high energy photons, most of the energy is given to the electrons. At diagnostic energies, which is low energy up to 150 keV, maximum energy scattered photon is at 511 keV. So this works in PET, positron emission tomography, at where the electron the photons can be emitted at 90 degree apart from the initial direction of the incoming positron, but that is annihilation in PET. But that being said, the maximum degree, the maximum energy, when maximum energy to the electron transferred at 180 degree, and maximum energy of the scattered photon is at 511 keV at angle 90 degree. So these two figures summarizes what happened with the photons, scattered photons and recoil electron during Compton scattering interaction. Alright, now that we have seen what are the most common interactions within the diagnostic energy range of photons with matters, in the next section we are going to have a look at how all these interactions being affected by the various tissues within human body, and how does this affect the formed images. How are the images affected differently based on Compton scattering and photoelectric interactions. Mainly Compton, because Rayleigh and Thomson only occur at low energy. Low energy is absorbed by added filter and inherent filter. So it's no use to talk about Rayleigh and Thomson in diagnostic energy. So we'll meet again to discuss the attenuation and absorption based on Compton scattering and photoelectric interaction of diagnostic energy range X-ray photons within tissue, and then from that we'll move forward to specifically discuss the scattered photons in radiographic imaging. Thank you.